All right, so today we'll jump into chapter 3. We did displaying data last video. I'm going to break this chapter up into kind of two different videos with Excel videos also associated with them. So with that being said, oh, let's get this going here. So how are we going to describe populations and sample data sets? We talked a little bit about the difference between those two last class. Or last video, sorry, gotta get out of that habit. We've got two real kind of beginner ways we're going to start out. The first is measures of central tendency, which I kind of already mentioned these in the last video, which things like the average, right? We're going to put some slightly different words to that, but really, I think probably at some point you've calculated an average of something in high school or already in college. So the three different measures of central tendency that we're going to have are the mean, the median, and the mode. So the way that we're going to kind of I'll start showing you notation is this Greek letter mu. So anytime we're looking at population data, we're going to write the statistics that we calculate using some type of a Greek letter, typically. So mu here represents the mean of population data. X bar, right, this is going to represent that we are looking at the sample mean. Sorry, we're looking at the mean for sample data. Okay? And then the median, kind of M subscript D, mode, M subscript O. We'll talk a little bit more about what these are here in a second, but just getting some notation out of the way. We're also then going to talk about not just where the central point of the data lies, but what is the variation that exists, right? If the average income in the US is 45,000, but there's $100,000 what we call standard deviations, what I'm talking about, but there's a lot of variation in how much people make. Well, we want to be able to capture that or calculate that as well. So the two measures we have there are going to be the variance and the standard deviation. So they're very closely related. So you'll notice the variance here for the population data set is this Greek letter sigma. So sigma squared. I guess I use my mouse. It's a little bit sensitive. So sigma squared. And then S squared represents the variance of my sample data. So sigma squared population variance, S squared sample variance. So we're going to calculate them. We'll see in the slightly different ways here in a second, but for now, we're just using notation. Now, the standard deviation, you'll notice it's still sigma and S, which means that the standard deviation is simply the square root of the variance. So we're basically just scaling the variance, and we'll see why down the road. Sometimes the standard deviation has a little bit more intuitive interpretations and has a little bit more use in some of our equations. So, we can calculate the variance. We automatically have the standard deviation. We just have to take one more step, which is take the square root. Okay. So how do we calculate the mean? Now, hopefully, if you're thinking about this, maybe you can skip this part of the video because hopefully you've calculated a mean before. This popped up. Try to edit this part out. Okay. I don't know if that even showed up on the recording. Hopefully not. But how do we calculate? So the mean, right? We said was for a population data set, this Greek letter mu, sample data, X bar. How do we calculate this? Well, all the mean is just a fancy word for the average. If you calculated an average before, what do? Well, you had, say, what's the average of 2 and 4? You would do what? Add those two numbers up and divide by the number of numbers you had. So 2 plus 4 is 6, divided by you had two numbers. 6 over 2 is 3. You do the same process when you have more numbers, right? I would just add up all of those numbers and then divide by however many numbers I added up. Now, the way that we'll write this kind of mathematically is going to be using something that you'll see pop up a lot in this class, which is this summation sign. So the way that we calculate our population mean is we will sum up, right, or add up, starting with the very first observation's value for X. So I equal 1, that means X1 would be the very first observations for the X variable you're interested in finding the mean of. You would then add the next observation's X value, the next one, all the way up to the very last observation in your population data set, which will indicate with capital N. So capital N here, we add up every single observation value for this X variable, and then divide by the number of observations we had. Let's just divide it by the number of numbers we have. This is calculating an average. That's all the mean is. So add up all of those numbers, all those X values for every observation, divide by the total number of observations you have. That'll give you your population mean. You could write this out instead of a summation, take the first observation's X value, add the second, the third, all the way up to the very last, and then divide by the number of observations you have in your population. So nothing too crazy here. So the sample mean, it's going to be the exact same thing. It's just that we're going to add up the values that we have in our sample data set, and we kind of make the distinction that capital N is the total number of people in our population or country, whatever we're looking at, right? The total number of observations in the population data set. We often only have a sample. That lowercase n is going to be a much smaller amount, right? Some subset of that population. But in practice, when you're actually going through doing the calculation, it looks no different, right? You're just adding up the number of numbers in your data, dividing by the total number of observations that you had. So if we're thinking about, maybe I had some like birth weight data, how would I find the mean birth weight? I would just add up every single birth weight I had in my data set, right? That's my numerator. And then the second step is, well, how many births were in the data set? I just divide that sum of all the birth weights by the total number of births in the data set, or my total number of observations. So I've got some data laying around. We can figure out it's about 3,200 grams. We'll work with this birth data and show it to you right now. So it's coming from some actual birth data from Indiana that we'll work with throughout the semester. Okay. So let's just look at a kind of easy example of how do you calculate a mean. Right? Well, here I'm going to just kind of look at, I've got some dumb game. This could be, I don't know, basketball, boggle, whatever it is. But I've got 7 games that were played and the score from this person for each game. What would the population mean for points scored be? Well, all I would do is go through, take 20, add to that 35, add to that 15, 18, 28, et cetera, et cetera. Once I've added up all of these points scored, I then divide by the total number of observations I have here, which is 7. Okay. So I'll add up all of those different, the first observation's X value, second observation's X value, all the way to the very last observation's X value. I then divide that sum by the total number of observations I have in my data set. Here I get the average score being about 23.86. So when I ask you to make these calculations, the homework, Excel files, generally we keep things out to the second decimal, right? And I'll often indicate, round your final answer to the second decimal. I think this one might end up being a little bit slightly different than 8.86, maybe like 0.861, or I forget exactly. Okay. In fact, let me kind of go back here. We'll look at a second example, and I'll show you actually how you could use Excel to calculate this without doing it like completely by hand. We won't use the built-in functions yet, which is how to use Excel as a calculator. So what if I wanted the population mean commute time? I've got some company named Asins, and I've got 7 different employees, and I've got their different commute times. All I'm going to do, once again, add up all these commute times, 20 plus 35 plus 90 plus 45 plus 40 plus 35 plus 50, divide by the total number of observations or employees I have, which is 7, right? So if I go ahead and do that, which is the following we're going to get here. Now, I gave you possible answers here. One thing I want to point out, if we're thinking about the mean, we don't want to lose sight, like getting too bogged down in our calculations. It should represent where the middle of the day, like where most of the observations values are, right? Well, if I'm looking for a middle point, it could never be higher than my maximum or lower than my minimum. So if I look here, if I did give you an answer that was less than 20 or greater than 90, right away, you can rule that out. You know that the mean has to be somewhere, right? It's supposed to be the middle point of the data. So somewhere in between that mean, minimum and maximum. Okay. I think if we actually calculate this here, we'll get exactly 45. Okay. Now, let me hit X here. Oh. There we go. You want to look at me. And actually, let me switch the video over so that it's on USB now. So I'm going to, I'm going to just copy this data. So Command C, Control C, PC. I'm then going to, over here, got an Excel file pulled up, but we'll just kind of start with a blank one here so I can show you what I would do. Oops. So let's say I have a blank Excel file pulled up and then going to blow things up so we can see it a little bit easier. I'm going to paste that data that I just copied. So how could I find this pretty easily in Excel? Well, one thing we talked about last class was I can find the sum of values by using this built-in sum function. So this is how we were calculating the number of observations when we were looking at those frequency distributions. So we can use that sum function. All I'm going to do is highlight the values that I want to add up. Now I can do this all in one cell, but I'm going to break it down into steps first and then show you can do it in all in one cell. So here's the sum of, so that's our numerator where we added up all the x values. What's the number of observations that we have? Well, we said one thing we could use as well to count the number of observations is just use the count function. There's no criteria, there's no if here, we're just counting. So I'm going to highlight these cells. So you can do it with your mouse or you can actually use your arrows to and then hold. So if I use my arrows, notice as I'm moving this around, once I'm got my built-in function, I've told it what built-in function I want to use, it'll be putting in the cell reference of whatever cell I'm in. If I go up to this first one and I hold shift and I hit the down arrow, it'll select all of these, right? So here, this should give me the number of observations. And then how do I find my mean? That's just the sum of all of my x values divided by that number of observations. Once again, I'm using the arrows, if I'm using the mouse, sum of all the x values divided by my observations. Sure enough, I get that mean of 45. Now you can also do this all in one cell just to kind of show this to you. So I can take the sum of all my x values and then divide it by, I could even get real crazy and do the count function. I know it's 7, but just in case I was working with a larger data set, sure enough, I get the same value. So I don't know, sometimes breaking it down into steps is a little bit helpful, just to, especially with like parentheses and order of operations, but you could do it all in one cell as well. Okay. All right, so let's go back here. Make sure I'm showing you the right thing. There we go. So we did our second example. Pretty easy, right? Well, what are the other two measures of central tendency that I mentioned? They were the median and the mode, okay? So the mode is just really going to be what value happens the most for that variable, or what value is recorded most often for that variable you're looking at. The median is going to be the value, and it sounds similar to the mean, but we'll see why it's a little bit different. It's going to be the value such that 50% of the observations are below it and 50% of the observations are above it. Okay? So I can imagine this might not be the case. So, well, we'll go through an example, then I'll kind of compare it to the median. So how do you find the median? We would basically want to arrange the data from smallest to largest, right? Figure out what the exact middle kind of observation is, if the number of observations are odd. If it's even, we're going to have two values left in the middle, right? How do we find the median then? Well, we'll just, whatever the remaining two are in the middle, we'll take the average of the two or the mean of the two. So what does this look like, right? So if I've got population data and I've got this point scored data set, what would the mode be? Well, I'm going to go through what happens the most. The only value here that happens more than once is 35. So that's going to be our mode, right? What's the median? Well, here I'm going to have to say, okay, I'm going to cross off the lowest, cross off one of the highest, then cross off the next lowest, then cross off the next highest. I'm going to go through in that process until I'm left with one value. The value that I'll be left with here is going to be in this odd numbered data set, this will be my median. Okay. If I did have, let's say I added in another one and I had like 20 and, oh, I don't know, let's say that I had an eighth game and it was 24 points scored. What would my median be? Well, I've got two values left, 20 and 24. I would just add them up, divide by 2 to find the average or the mean of 22. Okay. Just another example, kind of works through this. In fact, yeah, we'll look at the possible answers here. Once again, we don't want to get too bogged down here. The median, in fact, we know it has to be one of the values in our data set if we've got an odd number data set. Right? If we're finding the average between the two, maybe it wouldn't be, but with an even number data set, with an odd number data set, I know that I'm going to be left with one value. So if I don't have 47.5 as a value here, I know it can't be the median. Right? The median has to be one of the values I see here in my data set. So what am I going to do with this commute times? I'm going to cross off the highest, cross off the lowest. Let's see, do I have those? No. So another way I can do this, sorry. Well, I'll go through that and I'll show you this way. Cross off the highest, cross off the lowest, next highest, next lowest, next highest, next lowest. I'd be left with this value of 40. I could also arrange them, and then it's very easy to see, oh yeah, there's 3 observations to the left of 40 or below 40 and 3 observations above it. Well, that means that 50% of the remaining data is above it, 50% of the data is below it. That would be my median. So when you have lots of numbers, this process is very difficult to do, right? Because you're just gonna have a bunch of numbers that you have to cross out. But I'll eventually show you there's some easy built-in functions that do this for us in Excel, right? But this is how you would find kind of the median. You're looking for that value such that half of the observations are above, half of the observations are below. Okay. So if we want to compare the mean, the median, and the mode, I've got, there we go. I'm going to kind of draw this out. So just to kind of give you an idea about, oh, I don't know. Oh, actually, let's see here. I got to flip this and flip this again. There we go. Let's say I've got some X values. Let's make it easy on myself. 10, 20, 30, and 40, right? So I add these numbers up. I want to find my mean. I add those numbers up. Divide by the total number of numbers that I have. So I'm looking at this right. I've got what? 60, 100. So 100 over 4 should be 25. If I'm doing math in my head correct here. Now here, notice what's going to be my median? Well, it's kind of weird, but if I cross off the lowest, cross off the highest, I'm now left with 2 values in the middle because I have an even number data set. How would I find the median though? Well, if I have an even number data set, I take those remaining middle 2 values. Here I've got a data set where the median is exactly the same as the mean. Okay. So how is the median influenced by outliers differently than the mean? So let's say I had a second data set. Looks very similar. So 10, 20, 30, and oh, I don't know. Let's say I want to do 140. So most of the data is still the same. Most of the data is a relatively small value, but there's really one extreme outlier here. So if I'm calculating the mean, I would add those numbers up, divide by the total number of numbers that I have here, right? So that's what, 200 divided by 4. So I'm going to end up with a mean of 50. Okay, pretty high. What would my median be here? Well, if I go through the process, cross off the lowest, cross off the highest, I have 2 remaining. What's my median? Once again, if I have an even number data set, I just take the remaining 2 values and find the average. Notice here, the median is not affected at all by this extreme outlier, right? The mean, however, was like doubled in size, right? It was greatly influenced. So when we're thinking about the mean versus the median is going to be greatly impacted by extremely small or extremely large values. However, the median, right, because we go through this process, thinking about crossing off the highest, crossing off the lowest, it doesn't matter what this could be 1,000. it still only counts as one observation, as the highest observation. So the median is not impacted by these extremely large or extremely small values near as much as kind of our in this case, not at all compared to our mean. Okay. So what that means is when we have extremely high values, it's going to pull that mean to the right, right? Or increase that mean, but not really impact that median as much. Okay. So what does this look like? Go. So we sometimes can think of, because that median is not impacted, it can sometimes be a better representation of where the middle part of our data set is. So let's say I had an example, kind of like the one I showed you, the little toy example, where the mean is the highest point, the highest bar we had, the highest kind of category or bin that we had, that would be our mode. That's the number that happened the most often. The median, right? This would also represent there's 50% of the observations above and below it, and it just so happens to be also the mean, right? You kind of think about why, like every value on each side is like kind of counterbalancing each other. If we have right skewed data, so I kind of said the last chapter, it's if it has a long right tail. It's a very non-technical way of why. The real reason, the real characteristic of a right skewed data set is that the mean will be to the right of or greater than the median. Now, why? Because these extremely large values now, so before, we were only seeing values in this range. Now I've got some extremely large values. They're going to increase that median a lot, but not impact the median by very much, right? Because there's still just one observation. If I have left skewed data, what does that mean? Well, that means we said non-technical, it has a long left tail, or it's got extremely low values that are possible. Those extremely low values decrease the mean by quite a bit and don't impact the median near as much. So if the mean is less than or to the left of the median, you got left skewed data. If the mean is to the right or greater than the median, you've got right skewed data. So you don't even need to see the full distribution. If you just have these two statistics, you can tell whether or not the distribution is skewed one way or the other. Okay. Excuse me. Actually, let me just, as long as we're here, I'll give you kind of a shorthand way of thinking about this. All right. So anytime you've got that median being less than, I'll just write it out in words here. Oh, actually, let's use the notation here. So anytime I've got a mean that's greater than or to the right of the median, this is where we had right skewed data, right? There was extremely large values that were increasing the mean, but not impacting the median by very much. Anytime we have a mean that's less than our median, that means we're going to have really extremely low values that are decreasing the mean by a lot, and we end up with less skewed data. If we ever end up with them being exactly the same, we would kind of say this is a symmetrical distribution. Okay. Just kind of a quick shorthand way to kind of have that written down to remember that. And here I just comparing the values, right? If I was giving you these values or you calculated them from some data, you could tell if it has right or left skew. All right, so back to the slides. The next thing we're going to talk about is measures of dispersion, right? Or how much variation there is in the values that we're seeing. So, excuse me. Let's say the first one is just the range, right? All this is going to be is the difference between the maximum and the minimum value in our data set. You've probably heard this before. It's not that crazy. So I look at what's the highest value, what's the lowest value. The difference between the two is my range. So 90, 20 are my minimum and maximum. The range is 90 minus 20 or 70. That is, like I said, I think this is pretty easy, right? So we don't often, the range is just like a nice quick look at how much variation there is in the data. If I looked here and the commute time range was 70, I'd be like, oh, there's some people have shorter, a lot shorter commutes than others, right? 70 minutes is an hour. If I had a range of 20, well, that's telling me that people have more, pretty similar commute times, right? So the more tricky one to calculate, but I think once we see there's some built-in stuff in Excel and just kind of seeing this broken down, it's not too bad, is we're going to calculate the variance, right? So the population variance, we said we notate with sigma squared. Once again, we see the summation sign pop up. So we're just going to be adding up for every single observation, the value of that first observation's the value that the first observation has for this X variable, subtract the mean of that variable, then we're going to take that difference and square it. We're then going to go to the, second observation, take its value for this X variable, subtract the mean, square it. We're going to do that for every single observation. And then once we have them all added up, we're going to divide by our total number of observations. So we can kind of think about the variance is it's kind of like the average deviation from the mean squared. It's another way of kind of describing it. It's the average deviation of the data from the mean squared. Okay. And I'll break this down with some data here in a second. Sample variance, this is where we actually get a slight difference in the way that we calculate things. So with mean, didn't matter if it was population or sample data, it looked similar. Like the equations kind of looked similar once we had the numbers plugged in. Well, for the sample variance, it's going to be the same thing. We'll add up the deviations of every observation from the now sample mean squared. But once we add them all up, we're going to divide by not the total number of observations, but the total number of observations minus 1. And so have some implications for us down the road. When we start calculating things, there's a reason why we're going to do this, and it makes a little more sense. But for now, just kind of know the difference between population and sample data, I divide by n minus 1 if it's sample data. So we can think about what this is going to do. I can think about, the variance of the household income data, whatever the units of the variable are. I didn't say this before, but the units of the mean or the units of whatever variable you're calculating the mean for, the units of the variance are going to be the same as whatever you're calculating the variance, the units of whatever you're calculating the variance for. Before I break this down, I want to kind of make one point. So what does dividing this by n minus 1 instead of n do? So if I'm dividing by a smaller value, what that's going to do is it's always going to inflate my sample variance a little bit, right? Or make it a little bit higher. Dividing by a smaller number makes that fraction a little bit higher. So our sample variance is kind of like erring on the side of caution that we realize we only have sample data, right? There could be a little bit more variation if we had the population data. And so we're going to kind of, divide by n minus 1 here. So what are our steps? So first, we have to find the mean. So this is if I'm calculating the population variance. Then subtract the mean from every single observation. Square those deviations from the mean. Add them all up. And then divide. Okay, we really could have broken this up into 2 steps. You add all those square deviations up and then divide by the total number of observations that you have. We have a sample data set, then we're dividing by n minus 1. Okay. The population standard deviation, I'm not going to waste a lot of time on this slide because it's the exact same thing, because it's the variance, but then we're just scaling it. So notice these equations are exactly what we had before. It's just if I want the standard deviation, I need to take the square root, and just one more step. So, an easy way to think about this is, if I have a variance of 100, I would take the square root of that. The standard deviation would be 10. And once again, down the road, it'll be more obvious why we need this standard deviation. It has a lot more, it's easier to interpret once we get to things like confidence intervals and hypothesis testing. But for now, we just need to know that we can calculate the variance. And want the standard deviation, it's just one more step, which is taking the square root. Okay. All right. So, okay. So with the equations for the variance, now let's look at a sample data set and actually calculate it. Right? So let's say I've got this IU football coach salary data. So I put the link down here if you're interested. But these are in the thousands. So this head football coach is making what, 4.2 million? Geez. And then all the way down to the defensive tackle coach making 425. So we want to try to get a statistic that captures the fact that there is variation in these coaches' salaries. A lot of them are making similar values, but man, some of them are making a lot more. So we're going to calculate the variance to capture or give us a statistic that tells us how much variation there is in the data. So the first thing I'll need to do is figure out, well, what's the population mean, right? In order to find the variance, we said it's the deviation from the mean squared across every single observation and then divided by n, or the average deviation from the mean squared in our data set. Well, we can't find the deviation from the mean without first finding the mean. Should be pretty easy, right? We just add up all those different salaries from those 10 coaches, divide by the total number of coaches we had, which was 10. So we get 982 is going to be my mean. Well, what's the population variance? Well, what I'll do is take that mean of 982, take the first coach's salary of 4,000, come on, 4,250, subtract that mean, and then square that value. I'll then add to that the next coach's salary, subtracted the mean, square that. Right? Then take the next coach's deviation from the mean, squared, add that. I'll do that for every single coach. So kind of have it written like this, right? So the first coach's deviation from the mean squared, second coach's deviation from the mean squared, and then add them all up. And then I should be dividing by the total number of observations. I just wrote this a little bit differently. Sometimes I'll write this, instead of dividing by 10, I'm multiplying by 1 over 10. It's the same thing mathematically. The real honest reason why I do it is because if I try to write it as a fraction, I'll just show you. So I'm going to put this as my numerator. I'm then going to divide by 10. Notice, I mean, this, I can't put this all in one line and it just looks a little bit clunky. So that's why instead of dividing by 10, I just multiply by 1 over 10. It's the same thing. That should give me this variance, this population variance of about 1.2 million. Okay. All right. So back to the slide mode. So we've got our variance, right? Another way, just another visual of thinking about this is what I was really doing, and I could do this step by step instead of all on one line, just go through each coach, subtract that mean of 982, square it. Well, notice when there's a coach that has a really large deviation from that mean, that deviation squared becomes a really large value, like 10 million here. For coaches that were really close to the mean, right? This one was a difference of not even like 40. Well, that square is going to be a much smaller value. So, and that's because this observation was evidence to that in this data set, there is more variation from the mean. This observation was evidence that there isn't as much deviation from that mean. I'll then go ahead and do that for every single observation, add them all up. Once I add them all up, that's the sum of my deviation square, that's my numerator, divide by the total number of observations, I get that value of about 1.2 million. Okay. Now, one thing to point out here is, one thing that the variance does, notice this 10 million is way larger than 1,000. And in fact, it's way larger than the hundreds of thousands here. One thing the variance does, because we square that deviation, it really overpenalizes bad, like really big outliers, really big deviations. Think about it this way. If I square 1, 1 is still 1. If I square 2, 2 goes up to 4, 1 up by 2. 3 squared goes from 3 to 9 and went up by 6. 4 squared goes to 16 and went up by 12, right? That squaring that is going to make it so that if you see values really far from that mean, it really over penalizes that, right? Or it increases the variance by a lot. Okay. So this is a different way of thinking about the variance. I use the sample variance here just so we kind of get eyes on both of them. But I can actually rewrite my numerator of my variance as the sum of the x's squared minus n times the mean squared. So I'm going to prove to you why I can do that. I can also do this with the population variance. Notice it's just that I'm using mu instead of x bar. Okay. So I'm going to prove this. I'm going to show you the proof because I hate, when people tell me things and I'm like, there's no support. I'm going to give you the support for why this is true, but I'm never going to make you like reproduce this or even use some of these math rules that I'll mention here. But I think it's just kind of interesting to see some of this stuff. So let's say I had the sample variance and I just look at the numerator. Well, how can I rewrite this numerator? Well, it's going to be, this deviation squared. I could do xi times xi squared, xi times negative x bar, negative xi x bar, negative x bar times xi, negative xi x bar, negative x bar times negative x bar would be x bar squared. Now, anytime I'm summing up some things that are being added or subtracted, the summation can really be distributed in front of each of these. So that's what I'm going to do here. And I have my animation set off wrong, apparently. This is where we're going. We're trying to get to. So I'm going to rewrite this to just distribute my summation sign. I'm then going to do this little trick. Well, first, before I mention the trick, if I'm just adding up x bar squared, x bar is the mean. The mean is always the same value. So it would be like taking 50 squared plus 50 squared, or in this case, 982 squared plus 982 squared, doing that n number of times. I could just rewrite that as n times whatever that mean squared value is. Okay. I also then use this trick where if I multiply something by 1 over 1, doesn't change anything, right? Or sorry, 1 over 1. N over n, which is 1, doesn't change anything. So that's all I did here. Multiplied this by 1, or n over n. I'm then going to, anytime I have a constant, I can pull that out in front of my summation sign. So I'm just going to pull the n out and then rewrite this as xi over n. I'm then going to, the mean is a constant, so I can pull that out front. Notice here, I've got the sum of the x's over n. That's just my mean. So once I have the mean here, I can rewrite this as n times the mean times the mean. That's n times the mean squared, or n times x bar squared. Now notice that these two cancel, and I'm simply left with sum of the x's squared minus n times the mean squared. And then that was just my numerator, so I still have to divide it by n minus 1. Or once again, I can write that as multiplying by 1 over n minus 1. So just another way of calculating the variance, and we'll kind of see this kind of IU football coach data set. So let's say I had all my coach's salary. The first thing I'm going to need is, right, the sum of those x's squared. So I'm going to go through every coach's salary, square it, and then add those all up, right? So, oh, that's not right. Why is this value a little bit off? Oh, because I didn't change this. I was copying and pasting here. We actually add this up. Should fit that. There we go. Sorry about that. So if I add all those values squared up, I get about like what, 22-ish million, right? I then take the mean, which we had before, which is 982, square it, because one of the other things that I needed was, did I go too far back? Yes. Yeah, the other thing I needed was the mean squared, right? So I find that. I'm then going to plug everything in. So I've got the sum of the x's squared. I've got n, which was 10 times the mean squared. If I do that, I get about 12 million. Well, that's just my numerator. I still need to divide by number of observations, or 10. And sure enough, I get the same 1,215,000 that I found if I go all the way back to calculating it the other way. Okay? So it doesn't matter which way I calculate it, all right? I should end up with the exact same value, okay? So it's just a kind of a different way of calculating the variance. All right, so usually I would kind of give this as like a sample problem, right? If I wanted to ask you then, how would you calculate a population variance from a data set? So this is just a small sample data set, commute times that we were looking at before. What would I do? Well, I first need to find the mean. Remember, we calculated before, it was 45. I'd go through each observation, so 20, subtract the mean, so 20 minus 45. So take that value, square it, write that number down. 35 minus 45, square it, write that number down. Now, another thing that happens with the variance that I wanted to point out here, even though I didn't give you a potential answer, anytime I square something, it doesn't matter if the value is above or below the mean, because if it's below the mean, I'd have a negative value. But when I square a negative value, a negative times a negative becomes a positive. So every observation is always going to add in a positive amount to that variant, that numerator. Or at the very worst, it adds a 0 if the value is exactly the same as the mean, like in this case, right, 45. So if I gave you a negative value here, you know automatically that can't be the right answer because the variance can never be negative. Okay. From there, is it 0? Well, I've got values that are different from each other. I have values that are different from the mean. There's no way my variance can be 0. So now I know it's got to, be B, C, or D. Now, if I go through and actually calculate this, right, 20 minus 45, 25 squared is 625. 35 minus 45 is 10 squared is 100, et cetera, et cetera, et cetera. I add these all up, I get 2,900, divided by the total number of observations I have, which was 7, and I get 414. Okay. Now, I wanted to use this example to make then another point, right? So this should hopefully be something you could do by hand. If instead I said, well, look, actually, I don't have population data, this commuting time data set, I found out, oh, this is only some of the employees. It's just sample data. Well, if before, when I calculated this population variance, I found 414, I didn't even have to do this calculation. If I was given these 4 possible answers, I know what the new sample variance, or I know what the sample variance would be, because I'd use the exact same process, right? I would take the X value, its deviation from the mean squared. These are all the same values as before, so I'm still going to find 2,900. But instead of dividing by n, the total number of observations, when I have sample variance, I divide by n minus 1, or 6, dividing by a smaller value should give me this fraction should be higher. So automatically I knew if when I calculated this as a population variance incorrectly, I found a variance of 414. I know the sample variance I would calculate, I'm dividing by n minus 1 instead of n, I should find a higher value. Okay. So I just wanted to use this example to kind of point that out. Oh, how much? I'll go through this. So just kind of leads us into some things that we'll talk about. So here's like symmetric data. And they all have the same mean here, but the variance kind of tells us how spread out the distribution is. So notice here with this blue one, it's got a very low standard deviation or a low variance. That means that most of the values, right, the frequency of these values near the mean is very high, and the frequency of values that are very far from the mean is relatively low. Now, the higher I get my standard deviation, notice, well, these values start to become more likely, these values that are far from the mean, and then the values that are around the mean become less likely. Mm-hmm. So if I think about it, when my variance is getting higher, it's kind of squishing my distribution. Mm-hmm. So the variance kind of makes my, higher variance kind of flattens my distribution. A lower variance is going to make my distribution more peaked. Mm-hmm. And then if the mean changes, that's just going to shift my distribution along the x-axis. Okay. Kind of make a little bit more of a point about that. So let's say I had some distribution and it had a mean of 20 and standard deviation of, we'll say 10. Okay. Well, if I had another distribution and it had a mean of 30 and a standard deviation of 10, what I'd end up with is a distribution that's the exact same height. I try to draw the same height, but it shifts that distribution to the right. So anytime I have higher values, let me see here if I think I've got a better Sharpie. I accidentally grabbed a fine point one. Oh, this one's dying on me, but so differences in the mean just shift my distribution. Okay. If I've got different variances, right? So let's say I had a distribution mean of 20, standard deviation of 10. If I had a different distribution where the mean was 20, but it had a standard deviation of, I don't know, let's say also 20. That means that it's more spread out, right? The variance or the standard deviation is higher. That means that values near the mean are going to be less likely. Values further from the mean are going to be more likely, or I end up with kind of this flatter distribution when my standard deviation is higher. Okay, but didn't shift my distribution at all because the mean was exactly the same. So this is another way of thinking about how this, visually what this mean and this standard deviation do to our distributions. Right? And these are going to be similar to the distributions we looked at last class, these frequency distributions. So that concludes the theory. The next video, I'll kind of go through in Excel, dive into a little bit more about how we calculate the mean and the variance in Excel.